Okay. All right. Up until now, we've really talked about either descriptive statistics or we've talked about statistics that are comparison between group means or involved group means. And you know, the three basic scenarios we dealt with there were differences between two groups, say an experimental and a control group, that we used an independent t-test on and arrived at a decision as to whether those two means were significantly different from each other. In other words, they were had a less than 5% chance of creating false positives. Then we looked at differences between pre-post measures. Where often with one group, you'll have a sort of a pre-post setup where you do a pre-test, then you do some sort of treatment or intervention or instruction, and you do a post. And looking to see if there's differences between the pre-post means when it's viewed across the lens of just one group of subjects. And then we looked at when you have one group of subjects and you're comparing it to some sort of a population mean or some sort of a known quantity or a known grand mean to see if a particular group is significantly different from that grand mean or from that population mean. And that was the one sample t-test. Well, as often is the case, as can be the case, I guess maybe is a better way to say that, it is important to understand that not all scenarios play out as no more than two groups. That you have a lot of scenarios that play out as either more than two groups or as more than one independent variable, which involve categories. But because it's if you have say you have two independent variables and one dependent variable, one continuous dependent variable, you actually have four groups. Because if in the very simplest sense, if you have two independent variables, let's say one of them is gender and one of them is experimental and control, and then there's some test outcome. Well, if you have gender and experimental and control, both independent variables at play, that means you have four groups. You have a male control group, you have a female control group, you have a male experimental group, and you have a female experimental group. And so when you begin to look at multiple independent variables that you might want to look at in one analysis, you very quickly get beyond two groups. In fact, in the simplest of scenarios, you have four groups. And so it is important to have a scheme or a logic that we can use in terms of looking at more than two groups. And so the other dimension there is if we use, I suppose we could use independent t-tests to look at combinations between, more than two groups. But let's say we take the simplest of scenarios where we have two independent variables and we have four groups. We would have to look at, there's a formula for this, it's called n times n minus 1 divided by 2. And so if we had four groups, n would be 4, n minus 1 is 3, 3 times 4 is 12, divided by 2 is 6. We would have to do 6 separate comparisons with independent t-test. And if we did every one of those independent t-test comparisons, all 6 of them, and we did them all at a 0.05 error rate, less than 5% chance of false positive, that means across 6 of those, that error rate would accumulate. And so we would have, after doing 6 comparisons, we would have essentially a 30% chance of a false positive. And that concept is known as error rate inflation. And so we can't do independent t-tests simply because if we have more than two groups, the error rate gets too big too quick. And it becomes sort of meaningless to do the analysis. if you know there's a 30% chance or a 40% chance that that you could be getting it wrong, that you could say that something's going on here when it's just random error. And so we have to have a way of looking at more than two groups, and fortunately we do. And that way is called analysis of variance, ANOVA. I've put up some handouts on the on As You Learn, at least one good handout on As You Learn about ANOVA, and you can go on into the stats textbook that's referenced up in the resource section, and also look at a section on ANOVA and get a little bit more information about, the logic and the concept. But what I thought I would do is simply, do it on a kind of an overhead here in a very simplistic way, and not get into the, sort of the computational logic and things like that. So let me see if I can bring that up to share. All right, bring my overhead thing up to share. Okay. So let's say we have a set of numbers, and for the sake of argument, I'll not use real numbers for this. I'll just use indicators. So we'll do x1, x2, x3, x4, x5, x6, x7, x8, and x9. And so those are 9 separate numbers. And those separate numbers would give us, let's say they were divided, and we'll keep this example real simple. Let's say that those numbers were actually members of 3 groups. And so we had, the first 3 are part of group A, the second 3 are part of group B, and the third 3 are part of group C. And so we have 9 elements divided over 3 groups. Now we can look at, if you'll kind of remember back to the basic statistical thing, and we looked at what was called variance. Once we found the sort of the deviation scores between individual elements of something and the mean of that group, then we could square up those deviation scores, add them up, divide by n-1, and we would end up with what we call variance. Well, there's another term that can be used there, except it's calculated ever so slightly different. It's called mean square. It's essentially the same thing, except instead of using a n-1 degrees of freedom, we use n-2, because there are 2 sources of variance. There's a source of variance within the individual scores themselves, all 9 of those scores. If we figure those up separate as a set of numbers, there's a amount of variance associated with that. And there's also an amount of variance that's associated with each of the groups. So if we calculate, variance within each of the groups, we'll get a variance score for the groups. And since we use a different value in the formula, n-2 minus n-1 versus n-1, when we do that, we call it mean squares as opposed to variance. And so we might say that mean squares is the same thing. We call it MS. Mean squares is roughly equivalent to variance. It's just figured different. It's just figured differently. And it's n-1 for variance. It's n-2 for mean squares. All right. So for the set of 9 numbers, we could figure up a mean square for the total group of numbers. In other words, we could figure the variance when we looked at all 9 of those elements. And we found the mean, and after finding the mean, we found deviation scores between each of the elements and the mean. We squared those up. We added those up, found the mean, and that mean was what we would call mean squares. Now, we could also find the mean squares for group A, the mean squares for group B, and the mean squares for group C. So if we just looked at, say, the first 3 elements, this would be mean squares for A. We found the variance of that. The next 3 elements would be the mean squares of B, and the last 3 elements would be the mean squares of C. And those are all what we call within the group. And we could total those together. I mean, we could do a kind of a summation thing of those mean squares, and we get what's called mean squares within the groups, WG, or within group. Now, that mean square within the groups, we assume to be random error. We assume the mean square within the groups to be random error, because that's just random fluctuation within a group of individuals. Now, logic would supposedly tell you that the variance within the groups should add up to the total variance across the entire number set. It doesn't. In fact, the mean squares within the groups is always somewhat less than the total mean squares. And so we have to think about what's going on there. And if we think about this in terms of, say, circles, let's look at a circle. Let's say that this circle represents the total mean squares. Then there's 3 smaller circles within that, one of which is mean squares for group A, one of which is mean squares for group B, and one of which is mean squares for group C. And we know that their total mean squares within those groups does not add up to the total mean square. So what's going on? What else is happening here? Well, if you just think a little bit geometrically, or just, casually look, you know that there's other space within the big circle that doesn't lie within the little circles. And we call that mean squares between groups. Mean squares between groups. And we can't calculate it directly, but we can know its value, because if we take the mean squares total minus the mean squares within groups, the difference is mean squares between groups. And so by figuring out what those things are, we can create a new statistic. And the new statistic is what we call an F statistic. And the F statistic is equal to, remember, just like our t-test and just like the z-scores, on the top of the formula is a comparison, is a comparative. And that comparative is the mean squares between groups. And on the bottom of that ratio is an error term, an unbiased estimate of error. And that error term reflects the random error that's within the particular groups. So the F is the comparative, mean squares between groups, over mean squares within groups. And that gives us an F statistic. The F statistic has a distribution. It's a little bit of a different distribution, and it looks something like that typically. And somewhere in that distribution, there's a point at which 95% of all F values lies within this range, and only 5% lie out here. And if it's out here someplace, if our F is out here someplace, then we say there is a significant difference somewhere between these groups. The catch is we don't know between which groups. We don't know between which groups. So almost always when we do analysis of variance, we have to do what's called some sort of post hoc or post hoc testing that will allow us, once we have a significant difference, once we realize there is a significant difference between some groups, then we have to go in and figure out what is that difference and between which groups. And we use what are called post hoc tests to do that. And so this is looking at variance in a different way. In the t-tests and all, we're using variance as a way of calculating an unbiased estimate of error, whether it's standard deviation or standard error of the mean or standard error of difference on pre-post. But in an analysis of variance, we're using mean squares, which is somewhat analogous to variance. In other words, because of the difference in the n-1 versus n-2, it's calculated a little bit differently, has a little bit different logic attached, but we're using it to figure out how much of the variation within a set of numbers is contained within groups that we're interested in, which we assume to be random error, as opposed to differences between groups. And that's how we calculate whether there are significant differences or not. Now that's a lot, and it is a different way of thinking, a different scenario, but in some ways it's almost an identical scenario to what we had looked at earlier, because you end up with a comparative term on top of a ratio, an unbiased estimate of error on the bottom of a ratio, which gives you a statistic which has a predictable distribution. Now, there are two types of degrees of freedom here. There's a degree of freedom related to the total number of subjects and a degree of freedom that's related to the number of groups. And so if you think about degrees of freedom related to subjects, you count that by group, n minus 1, n minus 1, n minus 1, and then you count the degrees of freedom related to groups as number of groups minus 1. And so the total degrees of freedom always comes up to n minus 1 for the overall set. Any questions, thoughts? All right. What I'm going to do now is to do a JASP example. This example is up on your As You Learn page. And I'm going to do a JASP example of looking at analysis of variance first. Let me see if I can find that thing. There it is. Okay. Let me see if I can get that up and running. Okay, I'm going to put that up on a share. I loaded this directly into JASP. And let's see where we go here. Share. And have loaded a data set that's got 3 groups, A, B, and C, and scores for 3 groups on some test, some assessment. And so I'm going to use ANOVA as the basic test. So I select ANOVA. Score is going to be the dependent variable. Group is going to be the what are called fixed factors. That's the way you look at the independent variable or the grouping variable. Post hoc test, remember we need to do post hoc test if there's a difference. And so for this particular example, group is what I'm looking at to do the test on. I have to slide it over into the test. And I'm going to select or accept the default, the Tukey, which really assumes normality within the data set. And run that analysis. And so I end up with this outcome. Now, for the ANOVA, let me grab a pen here or something, a marker. For the ANOVA, a p-value is less than 0.001, so it is significant. There is a significant outcome. So we know that there are significant differences between the groups. We just don't know which groups. I don't know why it ran twice, but it gave me 2 outputs. So if we come and look at the post hoc test, in this case, it was what we called a Tukey test. The way this is set up is it looks at comparisons between groups. So it looks at comparisons between group A and B, between group A and C, and then between group B and C. And so the mean difference is calculated in the mean value for A minus the mean value of B, the mean value of A minus the mean value of C, the mean value of B minus the mean value of C. And since these are all positives, it means that A has the largest value, B has probably the next largest value, and C has the smallest value. If you look at the mean differences, you can kind of think that through. And so you look at significant outcomes. There is a significant difference between group A and B because the significance level is 0.005, which means that group A is significantly higher than group B. There is a significant difference between group A and group C in that group A is significantly higher than group C. Significance here is 0.001. But if you look at group difference between groups B and C, you see that this is not significant. It's not less than 0.05. So there is no significant difference between B and C. So the way you might interpret this is that there is a significant difference between groups A and B, a significant difference between groups A and C, with group A being higher in all cases, but there's no difference between B and C. So the real difference here is A is significantly higher than both B and C, but B and C are not significantly different from each other. And as I said, it ran twice, but I don't know exactly why. Okay, I'm going to stop the share. I'm going to save that particular JASP out. And that's the example for analysis of variance. Is there any questions or any comments? All right. Well, I'm going to roll right into, since it's about 8:36, I'm going to roll 6:36. I'm going to roll right into correlation and regression, and you can, we'll put this in one video, and that'll work pretty well, and we'll be done maybe in another 30, 45 minutes. All right. I want to go back to the PowerPoint that I used about basic statistical logic. And so I'm going to go in and share that up. Provided I can find it. Hold on just a second. Okay, there it is. And we're going to use that as a jump off. Okay. Let's say that we had we're looking at relationships between variables. These are considered to be continuous variables. And so that's important. In order to do correlation, we have to be looking at continuous variables. And let's say we had, among 7 subjects, we had data on their grade point average at their end of the first year in grad school and their GRE score in the analytics area. And so, for example, the first subject had an analytics score of 600, a grade point of 3. The group 7 had an analytics score of 700 and a grade point of 4. And so if we look at the means, we would find that there's a mean of 2.86 for the GPA, standard deviation of 0.69. There's a mean of 550 for the GRE score analytic section, and a standard deviation of 108. And so we have means, standard deviations for the 2 variables. Now, there's lots of ways to look at variables, relationships like that. The most elemental way is to look at them in terms of a graphic. And so if we, for example, here's that individual that had a 600 and a grade point of 3.0, represented by this dot. Here's that individual that had a 700 and a grade point of 4, represented by this dot. And so we could graphically plot these 7 subjects on a graph with different axes, GRE on one axis and GPA on the other. I know there are different scales, and we'll deal with that in a bit. But this gives us an idea of graphically what might be the relationship between GPA and GRE. And the more spread out these dots are, obviously logically, the less of a relationship. The more, say, focused these dots are, the more relationship that might exist. And so if we take the sets of dots and use the basic imperative in looking at sets of dots, we'll run a line through them. And this line is known by a couple different names. It's one, we call it the best fit line. Once we call it one, occasionally we call it the least squares line. But essentially it is the line that best fits all of these dots. And obviously they're not, all the dots aren't on the line because they didn't lie in a straight line. But it is a line where if you figure the distance between the line and the dots on one side of the line, added all that up, and then you figure the distance between the line and the dots on the other side of the line and added all that up, you would find that the 2 sums would be identical. And least squares means that, you know, we would essentially look for the smallest squared value, you know, between the 2 sets of numbers, and find the smallest squared value we could, and that means that line lies in what's called the best fit. Now, there are a couple of different perfect best fit lines. If you had a perfect positive relationship so that every time one variable went up 1 increment, the other variable went up 1 increment, you would have a 45-degree line starting at the axes and going up to the right. And that would be what we call a perfect positive relationship. Conversely, if we had a relationship in which for every incremental change in one scale up, we would get 1 incremental change in the other scale down. In other words, as one goes up, the other goes down, or vice versa. And that would also generate a 45-degree line, except it would start at the end of the values above the axes and go down to the axes, you know, getting to the axes at the value at the high end of the other scale. Now, there is an essential problem with this, and the essential problem is that these values are not on the same scale, and so therefore we have to figure out a way to get them on the same scale. And we have a way of doing that, and that's z-scores, because all z-scores lie on exactly the same scale, and that 68% of the values lie within one standard deviation or one z below and above the mean, and 95% of the cases lie within two standard deviations, two z's above and below the mean. And so we have a perfect symmetrical scale made up of z-scores. And so it doesn't matter what the raw score might be. Once we convert it to z's, they're all on the same scale. And so all we've done here is convert GPAs to z-scores, GREs to z-scores using their means and standard deviations, and multiply those together. Multiply the z-score values together, and we get what's called a product moment value. A product moment value. And I won't go into any detail about explaining what that means, but essentially the effect of it is that now we have dots that we can put on a scale that have exactly the same, relatively the same values on both the x-axis and the y-axis. And so those dots are in what are called product moments. If we find the average of those dots, we end up with a value. And this value in this case is 0.77. And that's called a Pearson product moment correlation value. Or we've simply shortened it to a correlation, Pearson correlation. The nomenclature for that particular statistic is what's called an R value. And that R value roughly describes the slope of the line that those product moments now describe. And so if we know that R value, and by the way, a perfect positive relationship, the one that starts at, at the axes and goes up at a 45-degree angle perfectly, the perfect positive least squares line has an R value, a maximum R value of 1. The perfect negative least squares line has an R value of -1. So all R values, all correlational values, lie between 1 and -1. A 1 has an equal strength of a -1. A 0.5 has an equal strength of a -0.5. The direction of the sign, positive or minus, really talks about the direction of the relationship. If it's a positive, that means that as one value goes up, the other value trends up. If it's a negative, that means as one value goes up, the other value goes down. And it's a negative relationship. And you have to know the nature of the variables to be able to understand or interpret what that might mean. If you're talking about the amount of, let's say the amount of exercise that you get and, your average daily weight, you might be interested in a negative correlation, because as you increase your exercise, you would hope that your weight goes down. If on the other hand, our blood pressure goes down as you do more exercise. On the other hand, if you're talking about your actual, if you're talking about the amount of time that's spent studying and your GPA, you might be more interested in a positive relationship because you would like to think the more you study, your higher your GPA. So as one goes up, the other goes up. So you have to understand the nature of the variables and understand what an R value means. Now, R values have a distribution. It's somewhat similar to the analysis of variance distribution. And it's only half a curve because negatives and positives in terms of strength mean the same thing. It's just the sign just tells you direction. And so each of those curves, though, is defined by degrees of freedom related to number of cases. So if you have a small number of individuals, it's going to take a larger R value to be significant. If you have a large number of individuals, it's going to take a smaller R value to find significance. And so R is very much susceptible to sample size, to N. And so you have to be somewhat careful with that. But you have to also understand that R's speak to relationships and not to cause and effect, or not to direction of effect. All you're saying that these two things are related to each other in some way. We do not know necessarily how. We need further evidence or more information or more evidence to kind of discern what that might be, but it speaks to relationship. These things are related or not related. Now, the other neat thing about this best fit line, if you think about the formula for a line that you had way back in elementary and middle school, it was something akin to or something similar to y is equal to mx plus b, where m is the slope of the line and b is the intercept point. This is also what's known as the regression line. And if you know the m and the b, you can plug in a value for x and predict what a value for y might be in that case. So if you have a significant relationship between y and x, as demonstrated by correlation, you can use x to predict y, or I guess you could actually use y to predict x, because you can know what the slope is, because you know the relative direction of the line based on the Pearson correlation, and you can interpolate the intercept because you know where the line lies on the scale. And so we could say that this line, the intercept is going to be somewhere along here, and the slope is defined by the speed at which it changes vertically versus the speed at which it changes horizontally. And so by knowing what this line looks like and having the R value, we can know the slope value and the intercept, and therefore we can, for a value of x, predict y. And that's called regression. And what regression allows us to do is to, based on one set of values that are related to, significantly related to another set of values, to be able to predict outcomes. And so, for example, if we were looking at GRE scores, we might be able to predict, based on your GRE score, X value, what your GPA would look like, and therefore factor that into your admission. Or we might be able to look at your income, X, and predict what's the likelihood that you will successfully pay off your loan on a scale of maybe 1 to 10. Or if we know your income X, what's the the appropriate amount of limit to put on a credit card? Or if you know your body mass index X, what's the appropriate number of calories to have for a daily intake? Or if we know the weight X, what's the appropriate dosage of a particular drug. And so this prediction model here, this simple little prediction equation that comes out of regression, can help us to make lots of decisions in terms of relationships that we feel that we know pretty well. And so, for example, if I apply the data that I already have, I already know the standard deviation of Y, standard deviation of X, in other words, GPA and GRE. That would tell me the M value is 0.0049. I know the B value is the mean of Y minus M times the mean of X, and that's 16.16. And so I can come up with a GPA equation that says, GPA is equal to 0.0049 times GRE plus 0.16. And so if I know, if I say know that a GRE of, let's say a GRE of 700, let me see if I can do that real quickly on my little handy dandy phone calculator here. So let's say I had a GRE of 500. And so 500 times 0.0049 equals 2.45 plus 0.16. And that would give me plus 0.16. What did I do? So what did I say? 500 times 0.0049 is equal to 2.45 plus 0.16, and that would give me a value of 2.61. So for a GRE of 500, I would predict a GPA of 2.61. And that's regression. Questions, comments? Okay. I'm going to go over on JASP now, and I'm going to run that correlation or regression example. Okay, let me share that up. Get my little marker here. And so I have a set of data that has group, gender, GPA, SAT, pretest, and post-test on it. And let's say I used I wanted to know whether there's a relationship between GPA and post-test value. I want to know if GPA is related to post-test value. Well, get this crazy stuff out of the way here somehow. And so I'll do a correlation matrix, a correlation, in which I will put in GPA and post-test as the things I'm interested in correlating. Do a Pearson, accept the defaults, report significance, and I find that GPA and post-test have an R value of 0.34, and they have a significance level of 0.034. Just an odd occurrence there, that it's the same numbers. Those are not connected in any way. And so it is a significant correlation between GPA and post-test score. So let's think about predicting post-test score from GPA, in other words, doing a regression. Linear regression. At this point, we're talking about continuous variables, so it's linear regression. I have to give it a dependent variable because it's the Y value, and so the Y value is post-test score. We want to predict post-test score. The GPA is our what's called a covariate. That's actually the predictor score. I want to make sure that we're getting everything we need. I haven't looked at these defaults. Okay, that should give us what we need. And so we go over and we look at the outcome, the output. We see that the ANOVA, it runs an ANOVA to check to see whether it's significant or not, even though this is regression. It has a p-value of 0.034. We knew that. We knew those two things were connected. And so, it's the same p-value as correlation. We have an intercept, what are called standardized and unstandardized coefficients. We're going to use the unstandardized coefficient. And I'm going to switch over to the overhead for just a second so we can talk about what this is, what this shows. Now, so remember these values, 58.594 for the intercept. I'm going to write this down so I don't forget. And GPA is 5.55. Okay. I'm going to stop this share and go share the overhead. And so these are the values. The intercept is 58.594, and GPA coefficient is 5.55. And so if we look at the formula, this is the Y is equal to mx plus b intercept. In this case, post-test score is equal to m, which is this value, 5.55, 5.55 times GPA plus 58.59. And so let's say we plug in a 3.0 in the GPA. So it's 5.55 plus a 3-point GPA plus 58.59. And so this is what, I'm gonna rough it here. I think it's 16.65 plus 58 0.59, and that's equal to 6874, 7524. I think that's correct. So for a GPA of 3.0, we would predict a post-test score of 75.24. And we pull those from these coefficients in linear regression. 58.94, 5.55. But once we've established that this is a significant predictor, 0.034, less than 0.05. So how do you interpret that? You say that there's roughly less than a 5% chance, less than 5% chance, 0.034, that if we predict post-test score based on GPA, that the values will fall outside of a particular range. And that range is defined by margins of error. And we'll talk about margins of error probably the next time we meet as to what those mean. So any questions, thoughts? All right, folks, considering that there's probably nobody here, I'm going to call it a day. You should have pretty much everything that you need in order to do the next set of assignments. There's examples for each one of those. There's an example, well, actually, you have examples for all of these. And along with these examples today for correlation or regression, you should be able to complete these assignments in the next couple of weeks. Now, I will be doing some follow-up, as I said, in the morning, once the, all the papers have shown up, or they're going to show up tonight. I will do a brief video that walks through the evaluation one, the correct answers, the interpretations, and what that should look like. And then I'll just kind of wait to see what questions you have, what problems you run into. You can always email me, call me, whatever, and we'll figure out something, work something out. If you're having problems with JASP, I'll work you through that too. But you're going to need JASP to run all of these things. Some of these things are just not doable on Excel or a simpler platform like that too easily. They're doable, but it's a lot more difficult to do. Okay, any thoughts, questions, concerns? All right, folks, I know this is a lot of fun, but some things in life are not fun. And I enjoy stats, by the way. I know I'm weird, but I guess it's that's what's enabled me to live a nice long life so far, is that I understand the odds against that, and I constantly every day get up and say, I beat the odds again. One of these days I'll win the lottery, probably right before I croak, but that's another story. And then my family will be taken care of for generations. So anyhow, it's just hang in there, work through these things. If you have questions or as I say, running problems or whatever, give me a yell, and we'll see what we can do. And look for the answer sheet and the brief video tomorrow. Going through the evaluation one. All right. Well, y'all have a good evening, and go do those things that we're all supposed to be doing in the evening, as opposed to be doing this. I was going to watch a baseball game, but then I realized that I looked at the score a while ago, and the Braves were already behind 11-0 in the second inning. So I figured that's not going to be much of a game. So maybe if I can stay awake long enough, I can watch the other game. We'll see how that goes. So y'all have a good evening, and I will see you in a couple of weeks. And once again, if you need me, give me a yell. All right. Have a good evening.